Alrighty, folks. We'll get started and get through this and get you guys to lunch. So, all right, this is going to be interesting. So way back in the beginning of programming, we had the way we programmed was putting instructions into memory locations, one right after another, and it was pretty painful. And is this picking me up all right? Okay. And so programs would execute one after another, one instruction after another. And then you had a special instruction that would cause execution to jump to another address. That was the infamous GOTO. And when I started programming, the first language I learned had literally had GOTOs. And it was a so-called higher level language as BASIC. But you had line numbers, and you actually numbered the lines of code. And when I came to learn Pascal, it's like, how do you know which line happens next? Because there were no line numbers. And then you had GOTO that would jump to another line in your program. That is a horrible way to program. It is awful. And so we came up with higher level languages and block structured programming, which took away the GOTOs. So you no longer had GOTOs. They were still there underneath the covers, but you had a number of higher level abstractions. You had while loops and for loops and the like. And then we came to functional programming, and we even got rid of those abstractions with higher order functions. You have a map, filter, reduce eliminates 90% of the loops in your code. Recursion eliminates the other 10. So what we moved from was this very low-level, simple concept of GOTO to jump execution to another place. We replaced that with a number of higher-level abstractions. And we kept moving up the stack as we abstracted farther and farther away from the machine, which is where the GOTO actually is rooted in. Okay, so that's that half of the background. But in this move,
are you having trouble with the video on the slides?
No.
Okay. Okay.
Yeah, I'm just.
Just to make sure you're good.
Okay, yeah, we're good.
All right.
I'm gonna have to keep. I don't know what I'm gonna do. All right, so that's one half of the background, and we moved away from GOTOs. And I mean, the GOTO wars were like, if you think we have arguments now about flame wars, GOTO wars were abysmal. I mean, they were bad. People hating each other because they either advocated for or against GOTO. And now it's just, we just know that they're bad. So anyway, the other flow control at the machine level is the conditional jump. And so you do an operation, and then you test the value of a single bit. And if that bit is set, you jump to a specified address. And if that bit is clear, you just go on to the next address. And that is the basis, that is the physical or the machine level concept of where booleans come from in programming. I mean, I know booleans are in logic, but in programming, it is this checking a single bit to do one of two things. And as we moved up the stack with higher level languages, we carried this baggage of checking a single bit along with us. And it is time for that to end. All right, so what do you replace the Boolean with? Well, I had a whole long explanation of maybe values, and I realized who I was going to be talking to. You just replace the Boolean with a maybe value, or nothing if in the case of false. And if you do Scala, I guess the option type is what you replace. So that is about half my talk just went away when I realized who I was going to be giving this talk to. You guys know what this is. You know what the maybe value is. So the abstractions, just like we replaced GOTO with the block structured programming and those higher level abstractions, the maybe value has the category theory abstractions, functor applicative, monad. Those abstractions are what we can use instead of resorting to the if expression. So what you have to do when you do that is you have to change also the functions that typically you think of as returning booleans. So instead, they return maybe values if they would normally return a true, and they return nothing if they would return a false. What that lets you do, and this is kind of the key point, is it lets you carry along information. You don't, like what he was talking about in the morning keynote, you don't just reduce all these computations down to a single bit. You can carry along information inside this maybe value. So if two numbers are not equal, then you just get nothing. But if two expressions are equal, then you carry along the result of that expression. And in the case of like less than, if they're not less than, oh, by the way, I'm a closure Lisp programmer, so that's why you see all the parentheses. Anyway. Okay, so then less than, if one number is less than the other, you can carry along the less than number. And so that's the change you have to make to the functions that return booleans. Okay, so then you have your combinators, the boolean combinators, or and. So you make them work with the maybe values as well. And my next talk right after lunch is on language I'm developing. And in that language, or and are the only lazy expressions. So they will short circuit. And in this case, if the first value is maybe, a maybe value, then that's the value that gets returned from the or. But if it's a nothing, then the second value gets returned. And if it's also a nothing, then eventually you run out of values and you just return nothing. And then and does the same thing. Any questions? Feel free to hop up. Yeah.
So before you were making maybes by doing a comparison, and now you're using the maybes for or. It's not or 15 9 gives you maybe 15. It's or maybe 15 maybe 9. So what's going on there? You know what I mean? Your or isn't like kind of lifting numbers into a maybe. It's just working on it.
It just works with maybe values. So if you had to do a type signature, or has to have maybe values passed into it. It cannot have any other value, any other type passed into it. Okay, so then any function that would possibly fail with a nil or a null, you return nothing in those cases. And in the other cases, you return, again, a maybe value containing, like in this case, first. It gets the first item of a list if it's not empty, and returns that item wrapped inside of a maybe value. And or if you check an empty list with the empty function, it returns maybe empty list if that list is indeed empty, and nothing if it's not empty. Okay. So then you have these functions that return maybe instead of booleans. Your filter, the typical filter higher order function, expects a function that returns boolean. So those functions have to be changed. And here are a couple of examples, or one example actually, the sum function. So sum is a function that takes a list and then a function that returns a maybe value, maybe nothing, and sees if that function will apply to any of the items in the list. And it will take, as a result, the result of the first item in the list that function evaluates to maybe for. So in this case, on the first example, it's calling empty question on ls, which is a list of lists. And so when you call empty on the first list, it's not empty, so it returns nothing. And so sum goes to the next list in the list of lists, which is empty, and calls empty on it, empty question, which returns maybe empty, which then becomes the result of sum. Clear? In the bottom example, none of the lists are empty, and so sum ls empty just returns nothing. Okay, here's the cool part. when I did this, I was like, oh, that is so awesome. So every is kind of a dual of, or a kind of a dual of some. It sees if a function will apply to every item in the list. So here is zipping multiple lists, any number of lists together. It's a recursive function. And by the way, I cut out a slide earlier. When you have a maybe value and you want the value inside of it, you use extract to pull that value out to get the plain value. And if you call extract on nothing, you get a core dump. So don't do that. Okay, so list zipper, that top function. To zip lists together, a zipped list is either an empty list if any of the lists that you're given are empty, or it's the rest of the lists, the rest of each of the lists zipped together with the first item of every list pulled out and concatenated into a list. And so that expression, there is no like, if you've hit the basis of your recursion, then do this branch, but otherwise continue recursion. The expression just reads like the definition of what a zipped list is. So does everybody get that? Cool. All right. And then zip lists is just a wrapper around list zipper that just extracts the zipped list. And you know it's always going to be a maybe value. You're not going to have that core dump problem, because if any of the lists are empty, then some list empty is always going to return a maybe value. So I had the example of how you would write this with if statements or stuff, and it's pretty ugly. If the first list is empty, or if the second list is empty, then you return the empty list. Otherwise, do the, and it gets kind of ugly. And when I saw this, I was like, that's awesome. So that was when my idea really hit home that, yes, this is possible. This really does work. Yes?
Are you saying that this method eliminates the recursion base case?
It doesn't eliminate it, but it allows you to express the base case kind of declaratively, because you don't have to think like a compiler and say, well, if this condition is true, then I'm going to do this. Or if it's not true, then I'm going to do this. You can just have the expression that defines what a zipped list is. Does that make sense?
Yeah.
Okay. Alrighty. So then you take one step up. You have maybe values. And with this crowd, I assume most of you know what monad transformers are. Cool. Saves me a lot of work. So yeah, you just compose the maybe monad or the maybe type with the state type, and you get the state maybe monad, which is probably the most useful monad. If you're ever going to learn one, it's probably that one. So I wrote the compiler for this language I'm developing using just the state maybe for like all of it, and eliminated all of the if statements that you would typically have in that kind of code by using the state maybe. And then in some cases, using the actual maybe value and then lifting it into the state maybe. But it worked. I was just pleased. Sometimes when I'm writing code, I think you're an idiot. And sometimes I think, man, you're a genius. And the difference, how the balance of that depends on what day it is. So yeah, any questions about this particular concept? Yes?
Which one is the base monad for the combination of state maybe?
Good question. I would consider the state to be the base monad because the resulting value in the state maybe monad is a maybe value with a pair inside of it. So that's what I would consider. But other people, I think, would consider the opposite. So your guess is as good as mine, basically. I have my preferences, but so state, but it would be like state T, maybe, would be the. Okay, so I got rid of all those if statements except for one. Literally, I had one case where I had to check a condition, and then on the basis of that condition, 4 different places in that little function, I had to choose between 2 values. And it just irritated the heck out of me. I was like, okay, come on, I'm so close. What is the last secret? And then I was standing in the shower, and I remembered another talk that somebody had given, and it was this: make maybe values implement function semantics. And so in this case, big or small, and this is a little bit unclear. I could have maybe broke it out a little bit more, but big or small is a function that takes an x and compares to see if x is less than 20. And that comparison expression, remember, returns a maybe value or nothing. And then that value is used as a function, and that function is passed 2 values, small and big. So the first value that gets passed in is what that expression returns if the value is true, is a maybe value. And the second value, of course, is the false. Now, in Haskell, with a lazy evaluation, lazy semantics, you could put tons of code in these 2 different values, and they would only get evaluated if they need it. In my language, it's strict. And I specifically, want that. So this particular case is limited or intended to be used when those are literal values. You're trying to select between 2 literal values, because they will both be executed. Both expressions will be executed every time the function is called, which is probably not what you want if they're complicated function calls or whatever. So it's a way of discouraging the use of this kind of expression to only those places where you really, really need it, and you're selecting between 2 literal values. So that's a design choice that I made. And that's it. With that last piece, I pretty much eliminated any use of if statements or cons or whatever your flavor is in the code that I'm writing to implement this new language, the compiler and the parser and the analyzer and everything. There are some of those do an expression to get a maybe value and then extract the inner value out of that. There are some of those cases in the core library at the very bottom level. But outside of that, the use of extract is a key or a clue that you need to refactor that code. Use comprehension, monad comprehension, or use an applicative, or do something else. And so for me, I'll sit down, I'll just bang out the code. I'll say extract this value, whatever, because I still have the reflexes of using booleans. But then I can just do a search on my code and look for extract. And it's like, oh, that's ugly. And then how can that be moved out into something else? How can that be refactored? And so what that has let me do is think at a higher level. So I can take that value, that expression, that maybe value, and put a name on it and name it. And that name can carry information to me as the programmer that then it plugs into other functions quite well. And so it's a way that I found of letting me see what the code is supposed to do and communicating to myself, my future self, this is what this code is supposed to do. As opposed to every time I come to one of those expressions having to play compiler and saying, well, if this condition, which comes from here, is true, then I'm going to have to do this. And so it really has made not a life transformation, as a programmer, but it has made the code much nicer that I've been working on. I've been really pleased with the results of this little crazy idea I had a couple of years ago. So that is the talk. That's me on Twitter. So that's it.
Can you give it? You talked about not losing data, like in
was
Mhm.
to produce the just. Can you give an example, like a canonical example, if you have one, where that is really useful down the line, where I got a just instead of a true, and I'm really glad that I have the result of the thing that produced it here in the just.
Did you come in late? Did you see the list zipper example?
Zipper, yeah.
Yeah. So that was the one that I was most pleased with. But yeah, anytime like you're doing maybe finding a min in a list of numbers, you could just reduce down. Well, that may not be a great example.
So it's in cases where it's like, you want to know that it happened, and you want to know what the answer was. You need
Yeah.
both of those at the same time.
Yeah, those are the cases. But it does give you the flexibility of putting anything in there you want. So you don't, you can just pile all kinds of information in there, stack traces or whatever.
I'm just wondering, this might help your question. I'm wondering, was this inspired by or kind of formalization of, like in sort of classical Lisp, predicates usually return nil or a useful value, right? And this is like digit p, for example, in common Lisp returns the digit of a character or
Mhm.
nil if it's not a digit. And this is actually really handy because then you can often chain things together with or in common Lisp exactly as you're doing, except it's not, except it breaks when you actually want maybe nil, for example.
Yep.
And it's a little less formalized, but it's very similar kind of idea. It's actually very useful.
Yeah, I'm a closure programmer by day, and in there, nil can be false, and so functions, predicates can return a value which would evaluate to true, or nil. And I hate nil. I hate null pointer expressions. And so this was kind of my way of eliminating the use of nil.
Well, so first off, I'd say probably an answer to the previous question is that something like a safe head is a case where you want to be able to do this. You have a failure case, but also a value case. The thing that I would ask, the reason I was less inclined to go down this road myself is, so like JavaScript has infectious nil, where oftentimes, if you do like nil plus 5, you get nil back, and so then nil will just sort of infect outward. And I'm pretty sure applicative on maybe does the same thing. You get nothing infecting outward. The thing that seems kind of a bit bad about that approach is it becomes trickier to debug then, because or even to diagnose, because somewhere something failed, but you don't know what or why. So I mean, maybe going to the either approach, and then like proliferating data types or enumerations to indicate value cases could help. But then at that point, aren't you just like re-implementing if, but like with slightly vaguer semantics?
Well, yeah, I mean, just like we didn't get rid of goto, it's still underneath the covers.
Right.
If and friends are still underneath the covers. So you're not eliminating, but at the level that I live at and I program at, they're hidden. So, but yeah, exactly. Using either to carry more information on the failure case, or even having 3 different types. Maybe failure or nothing, like he was talking about this morning, or 10.
Maybe I should be a bit clearer about what I mean by that. So say you have a text box and you want to validate the input from it. There's often many reasons that it will fail, and you also need to report the reason that it failed to
Sure.
the user.
Sure.
So in that case, replacing if with applicative maybe has the problem that you can't really implement that.
Sure.
So, and that tends to be, I think, probably a more common, at least in terms of, I think that's often a more common pattern than just the thing that you're talking about.
Sure.
You mentioned
Yeah.
either, but also like result has become really popular in the OCaml world lately. A lot of like libraries are built around returning result, which is basically either, which is you have your success case or your failure case that tells an error message around for debuggability.
Did I see a question, a hand over here somewhere? Dang. Did you have a question, or?
See, I was just wondering about the when you're talking about the sort of functional semantics for the maybe and nothing. So is that basically remind me I kind of know like the chicken like a lot of LambdaConf formalizations where you have you formalize like true as lambda xyx and false as lambda xyy. Like
Yes.
xy,
Yes.
y,
Yes.
exactly, basically, right?
Okay, so let me give a disclaimer. my career up until I found functional programming was as an embedded programmer. So I push bits. And so when you say formalized, is this a formalization of internally I'm going, heck if I know. So, but yes, that is kind of it. Yeah.
I was wondering if you looked at your code before and after, and did you find that it was shorter or lower complexity?
Yeah, it seemed to me to be shorter and less complex, more declarative in that list zipper example.
Did you like measure it?
No.
Report it?
No, I
Do
was.
you have the old copy that you could say?
It's back there in a commit somewhere.
Worth knowing, because it looks like what you want to do is you want to code your happy path, and you hope that the special cases and the errors are not 80% of your program.
Mm-hmm. Yep,
And
which
it
they
seems
usually
like
are.
You shorten the amount of code that you'd rather not have to think about.
Mm-hmm.
And it's focusing on the code that is sort of the programmer's intention and letting the special cases
Yep,
work their way out.
on the left.
Is this language out on open source, or what's the name of it?
Yeah, come to my talk after lunch. The next great functional programming language, which I did not choose that title. That was chosen for me. I just want to make that clear. Yeah.
So I wanted to suggest a way of thinking about what you're doing. I was, a little confused as to what are these return values supposed to be, right? Like if I'm writing a function that normally would return a boolean, what should it return, right? And an explanation that seems to fit a lot of your cases, though not all of them, is that what it should return in the true case is evidence that the proposition is true, right? So that works, for example, with your sum function and a number of others. And it relates nicely to logic because, whereas if you have just true and false values, that's Boolean logic. There's another kind of logic called constructive logic where your truth value is either falsehood or evidence that the proposition is true.
Sure. Yeah, what he was talking about this morning, which it's formal stuff, and I was like, I need to look at that. All right, let's get some lunch.